As carbon emissions continue to threaten Earth's future climate, it's become increasingly necessary to find new methods to manage and maintain CO2, rather than releasing it into the atmosphere. Now, researchers say the key to safe, long-term storage may be hiding deep underground. According to a new study, reservoirs more than half a mile beneath the surface are capable of storing CO2 for over 100,000 years without corroding the rock above, 10 times longer than the time needed to avoid climatic impacts. Though earlier studies have suggested that underground CO2 can corrode meters off the overhead cap rock which contains it, new research at a natural reservoir in Utah has found that the buried carbon may actually shave off less than 3 inches in a period of more than 100,000 years. This means that the greenhouse gas is unable to leak back out into the atmosphere, according to the findings, published today in the journal Nature Communications. The Cambridge-led researchers say this form of storage may be far more secure than previously thought, indicating that the process of carbon capture and storage, CCS, may be a viable solution to reduce emissions from coal and gas-fired power stations. This method involves the capture and compression of carbon dioxide, which is then pumped into reservoirs deep underground. Carbon capture and storage is seen as essential technology if the UK is to meet its climate change targets, says lead author Professor Mike, director of the Cambridge Centre for Carbon Capture and Storage at the University of Cambridge. A major obstacle to the implementation of CCS is the uncertainty over the long-term fate of the CO2 which impacts regulation, insurance, and who assumes the responsibility for maintaining CO2 storage sites. Our study demonstrates that geological carbon storage can be safe and predictable over many hundreds of thousands of years. In order to avoid harmful effects to global climate, underground carbon must be securely stored for 10,000 years. The researchers, funded by the UK Natural Environment Research Council and the UK Department of Energy and Climate Change, drilled deep into a natural reservoir, where CO2 has been trapped in the sedimentary rocks for hundreds of thousands of years. Analyses on samples of the rock layers and fluids within the rock pores revealed that the CO2 led to very little corrosion of the minerals in the cap rock, with this effect seen in a layer just 7 centimeters thick. The data from the site was combined with computer simulations, showing that the layer took at least 100,000 years to form. Some earlier studies, using computer simulations and laboratory experiments, have suggested that these cap rocks might be progressively corroded by the CO2-charged brines, formed as CO2 dissolves, creating weaker and more permeable layers of rock several meters thick and jeopardizing the secure retention of the CO2, Bickel explains. However, these studies were either carried out in a laboratory over short timescales or based on theoretical models. Predicting the behavior of CO2 stored underground is best achieved by studying natural CO2 accumulations that have been retained for periods comparable to those needed for effective storage. Storing CO2 in underground rock reservoirs necessitates an impermeable cap rock to ensure it won't escape. The gas is compressed and injected as a dense fluid, but it is less dense than the brines which fill the reservoir pores, and will continue to rise until it hits a secure barrier. With careful evaluation, Bickel says, burying carbon dioxide underground will prove very much safer than emitting CO2 directly to the atmosphere.